the last lecture we had done the modal analysis of optical fiber and we had obtained the transcendental equation satisfied by the propagation constants of the modes. We had also seen the cutoffs of various modes. Now, in this lecture we will extend the analysis and see how the modal fields look like. So, this is the step index fiber which we are analyzing, which has a high index core of refractive index n1 of radius a and the cladding of refractive index n2, and we had done this that the radial part of the modal fields is given by AJL UR over A in the region R less than A, which is the core, and BKL WR over A in the region R greater than A, which is the cladding. We had also defined the normalized frequency V, normalized propagation constant B, and U and W are defined by these relations, and you can also express them in terms of normalized parameters V and B. So, we had seen that the propagation constants of the linearly polarized modes of this fiber satisfy these transcendental equations or the eigenvalue equations. So, after solving these equations for a given value of V, I can find out the propagation constants B of various modes of the fiber, and if I plot them as a function of V, so they look like this. So, this we had done. Now, let us look at how the modal fields look like. So, the total modal field would be given by the radial part and the angular part or azimuthal part. In phi direction, I can have solutions cosine L phi and sine L phi, and I label these two solutions by two different names. I call cosine L phi solution as even mode and sine L phi solution as odd mode. Now, let us look at the modal fields of LP01 and LP11 modes of this fiber. So, since we are looking at LP01 and LP11, which means here L is equal to 0, here L is equal to 1. So, in the core I will have solution for LP01 mode as J0 UR over A, and for LP11 mode J1 UR over A. So, let me plot J0x and J1x, they look like this. In the cladding I will have the solutions K0 WR over A and K1 WR over A. So, let me plot how K0x and K1x look like. So, when I combine these, so in the core I will have this solution, and in the cladding I will have this solution, and since these are the first modes of L is equal to 0 and L is equal to 1 respectively, so I will not have any 0 in this, and I will not have any 0 in this except a 0 at R is equal to 0. So, for LP01 mode in the core the field will go like this, and in the cladding this function will take over. For LP11 mode the field in the core would be given by J1, so it would go like this without any 0 except a 0 at R is equal to 0, and then this K1 function will take over. So, this is how the radial part of the modal fields would look like. What about the angular part? Angular part is simple. For L is equal to 0, you have cosine L phi is equal to 1, and there is no contribution from sine L phi because it would be 0 everywhere. So, I will have only this kind of solution. So, you take this in radial part and then you go in angular part, rotate it in phi direction, and you will get this kind of variation. However, for LP11 mode I can have cosine phi solution and sine phi solution. So, if I take cosine phi solution, that is at phi is equal to 0 I have a maximum, and then phi is equal to pi by 2 I will have 0, okay, and so on. So, if I rotate it like this in phi direction, then I will get this kind of variation, this kind of density plot or intensity pattern. If I take sin phi solution, then sin phi would be 0 at phi is equal to 0, and then it would be maximum at phi is equal to pi by 2, and then if I now rotate it, so it would be 0 at phi is equal to 0, it would be maximum at phi is equal to pi by 2. So, it will give me this kind of solution. So, L is equal to 0 mode will only be of this kind, that is I cannot have two-fold degeneracy for L is equal to 0 mode as I can have for L is equal to 1 mode here, or L is equal to non-zero mode, L non-zero mode. I can look at the 3D plot of these. So, if I look at the various modes, so this is how the LP01 mode would look like, and if you view it from the top, it would look like this. LP02 mode will admit 1 0 because it is the second mode in L is equal to 0 series. So, it will admit 1 0 in the core. So, it will go down. This is the intensity plot. So, if you look at it from the top, it would look like this, and there would be a 0 at r is equal to something here, okay, in the core itself. If you look at LP11 mode, it would look like this, okay. It would not have any 0 in r direction except a 0 at r is equal to 0, and these are this is the plot of even mode, even LP11 mode. So, if I again look at these plots, now I have LP modes here, linearly polarized modes. It means that I can have two independent or orthogonal polarization states. I can label them as x polarized and y polarized, okay, because z is the direction of propagation. So, I can label them as x polarized and y polarized. So, if I look at LP01 mode, then it can be x polarized or y polarized. So, this LP01 mode is two-fold degenerate, and it does not have any 0 in r direction. If you look at LP11 mode, then I can have cosine phi solution, and in cosine phi solution itself I can have two polarizations, y polarized and x polarized, and I can have sin phi solution. So, there also I can have x polarized and y polarized. So, it would be four-fold degenerate, and again there would be no 0 in r direction except a 0 at r is equal to 0. If I look at LP02 mode, then LP02 mode would again be two-fold degenerate. You will have x polarized and y polarized. If you look at the second mode in L is equal to 1 series, that is LP12 mode, then it will have 1 0 in r direction except a 0 at r is equal to 0. So, the modal fields would look like this, and again this would again be four-fold degenerate. This is LP21 mode. Now, in LP21 mode, because L is equal to 2, so L is equal to 2, though, so the phi solutions are cosine 2 phi and sine 2 phi, and they will have 4 zeros in phi directions that you can see here, and in x direction there would not, in r direction there would not be any 0 except at r is equal to 0. So, this is how the modal fields would look like for even and odd modes. So, in general what I get for LP-LM mode, the number of zeros in phi direction would be 2L, and the number of zeros in r direction would be m minus 1. except any 0 at r is equal to 0. So, if I have various modes, I can immediately find out the number of zeros in r and phi direction. For example, in LP21 mode, there would be 4 zeros in phi direction and no 0 in r direction. I always exclude a 0 at r is equal to 0. For LP31 mode, I will have 6 zeros in phi direction and no 0 in r direction. For LP54 mode, I will have 10 zeros in phi direction and 3 zeros, 4 minus 1, 3 zeros in r direction. So if I know any mode, if I am given any mode, then I can immediately find out the number of zeros in phi and r direction, and I can also plot the intensity patterns of those modes. For example, these are the intensity plots of various higher order modes. This is LP32 mode. LP32 mode will have 6 zeros in phi direction. So, I have 6 zeros, 1, 2, 3, 4, 5, 6 zeros in phi direction and 2 minus 1, that is 1 0 in r direction except a 0 at r is equal to 0. LP43 mode will have 8 zeros in phi direction and 2 zeros in r direction. LP54 mode, 10 zeros in phi direction and 3 zeros in r direction, 1, 2, 3. LP63 mode, 12 zeros in phi direction, 2 zeros, 3 minus 1, 2 zeros in r direction, and so on. So, if I am given any mode, then I can immediately draw the intensity pattern corresponding to that mode. Now, the question is, how do I estimate the number of modes here? Okay. In planar waveguide it was easy. I just calculate the value of V, divide that value of V by pi by 2 and find out the closest but greater integer, and that will give me the number of modes. Here the cutoffs are not evenly spaced and there are several series corresponding to L. So, where do they fit? I do not know immediately. So, what is the procedure of estimating the number of modes here? So, the first step is the same. You first calculate the value of V. So, if you are given a fiber and the wavelength, first you calculate the value of V, then you find out the cutoffs of various modes using the cutoff conditions and the zeros of Bessel functions. So, if you have the zeros of Bessel functions and cutoff conditions for various modes, you know, for L is equal to 0 mode, the cutoff condition, for L not equal to 0 cutoff conditions, which are in terms of the zeros of Bessel functions. So, you find the cutoffs and then arrange the modes in the increasing order of their cutoffs. So, for example, the fundamental mode LP01 mode has 0 cutoff, LP11 mode has 2.4048, 3.8317 is for LP02 and LP21, 5.1356 is LP31, 5.5201 is LP12 and so on. So, you arrange them, arrange the modes in increasing order of their cutoffs and then locate the value of V here, okay, and find out how many modes are above that value of V, and those would be the number of modes supported by the fiber. Let me work out an example. If for a given fiber and given wavelength, I calculate the value of V and it comes out to be 5.3, then I locate this 5.3 in this table which is here and I count the modes above this. So, 1, 2, 3, 4, 5. So, these modes LP01, 11, 02, 21 and 31, these modes are guided. I can also find out the total number of modes by including their degeneracies. I find that there are 2 modes which have L is equal to 0. So, they will be only 2-fold degenerate. So, they comprise of 4 modes, and then I have 1, 2, 3 modes which are L is equal to L is equal to not 0, L not equal to 0. So, they will have 4-fold degeneracy and they will comprise of 12 modes. So, I will have 12 plus 4, 16 total modes including the degeneracies. So, this is how I can calculate the number of modes. Of course, if V is less than 2.4048, then there would only be one mode supported. Of course, there would be it is 2-fold degenerate. So, rigorously it supports 2 modes corresponding to 2 polarizations, but as a convention I call it single mode fiber, okay, because for a given polarization it has only one mode. So, for V less than 2.4048 I have a single mode fiber, and this is how the cutoff condition for single mode operation is coming, because 2.4048 is the cutoff of first higher order mode, which is the LP11 mode. If V is much larger than 1, typically more than 10 or around 10, then the number of modes can be estimated using the approximate formulae which are given as for a step index fiber. The approximate number of modes are V square by 2, and for a graded index fiber which power law profile, which is characterized by profile parameter Q, the number of modes can be estimated by half of Q over Q plus 2 times V square. So, if it is parabolic index fiber, then Q is equal to 2, then the number of modes would be V square by 4. Let me work out some examples. Let me consider a step index optical fiber with core refractive index N1 is equal to 1.45, cladding refractive index N2 is equal to 1.44 and core radius 8 micron. And I want to find out the total number of modes including degeneracies supported by the fiber at lambda naught is equal to 1.5 micrometer. So, the procedure is very simple. You have to first find out the value of V. If you find out the value of V for these parameters, then it comes out to be 5.697. If you locate this value of V in the table which you have created by arranging the modes in increasing order of their cutoffs, then you find that these modes are supported LP01, 11, 02, 21, 31 and 12. Now, if you include the degeneracies of all these modes and calculate the total number of modes, then they come out to be 20. So, with this value of V, the number of modes would be around 20. You can also see that if you calculate using V square by 2, V square by 2 would roughly be because it is 6, it is close to 6. So, 6 square is 36, 36 divided by 2 is approximately 18. So, little more than 18 and here you are getting 20. So, they are close. Second is the wavelength at which the fiber is single moded. If I want to find out the wavelength at which the fiber is single moded or the wavelength range in which the fiber is single moded, then I know the single mode condition for a fiber is V should be less than 2.4048, and I have the expression for V which goes as V is equal to 2 pi over lambda naught times A times square root of n1 square minus n2 square. So, if I find lambda naught from here, then I will see that for lambda naught greater than 3.55 micrometer, V would be less than this, and therefore, in this range of wavelength the fiber would be single moded. Third part is approximate number of modes at lambda naught is equal to 0.5 micrometer. So, I again calculate the value of V at 0.5 micrometer, and it comes out to be about 17, which is much larger than 1. Then I can find out the approximate number of modes by V square by 2, and it comes out to be about 146. So, this fiber will support 146 modes. Now, let me work out some examples on identification of modes from their given intensity patterns. How do I identify various modes from their given intensity patterns? So, let us look at this. This one is easy. If I go in phi direction, I take any value of r and go in phi direction, I do not encounter any 0. So, the number of zeros in phi direction is 0, which means 2L is 0, which means L is equal to 0. Second thing I do is I count the number of zeros in r direction. So, I take any value of phi, and for that value of phi I move in r direction, and I encounter 1 and 2 zeros. The number of zeros in r direction is 2. So, m is equal to 3 because m minus 1 is equal to 2. So, this mode is LP03 mode. Similarly, for this mode the number of zeros in phi direction, is 4. So, 2L is equal to 4, L is equal to 2, and number of zeros in r direction, you exclude 0 here. So, it is only 1. So, m minus 1 is equal to 1, which means m is equal to 2. So, this is LP22 mode. Similarly, here it is LP51 mode, and this is LP32 mode. So, in this way I can identify any mode. Next example is schematically draw the contour intensity plots or density plots of these modes, and I just want to draw the patterns of even modes. So, cosine L phi solution. So, let me do it for LP21 mode. So, for LP21 mode what I have, L is equal to 2. So, number of zeros in phi direction are 2L. So, they are 4. So, now where these 4 zeros are located? Okay, I know that if you go in phi direction, then phi ranges from 0 to 2 pi. Okay. Now, you have solution which has cosine 2 phi. Okay. So, you now find out the zeros of this cosine 2 phi. They will occur at pi by 2, then 3 pi by 2, and where do you stop? You stop because phi goes up to 2 pi, then 2 phi will go up to 4 pi. So, until you cross or reach 4 pi, you do not stop. So, 3 pi by 2, 5 pi by 2, and then 7 pi by 2. After that it would be 9 pi by 2, which is more than 2 pi. So, you stop here. So, here these 4 zeros would be located, which means phi is equal to pi by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4. So, here you have 0, this is pi by 4, this is 2 pi by 4, this is 3 pi by 4, 4 pi by 4, 5 pi by 4, 6 and this is 7 pi by 4. So, here you have 0 and in between you will have the intensity and m is equal to 1. So, there would not be any 0 in r direction except a 0 at r is equal to 0. So, you will have intensity something like this. Okay. So, this is how you will plot the intensity. So, this is how it would look like. Similarly, for LP32 mode, you will have 6 zeros in phi direction and you can, in the same way you can calculate the values of phi where the zeros will occur, and since m is equal to 2, so there would be 1 0 in r direction. In the same way you can plot for LP41 mode and LP13 mode. So, today we have learned about the modal fields. In the next class, we would look into what fraction of power of these modes is confined in the core and about various parameters of a single mode fiber. Thank you.